Yeah, that one. Something like that. Here's that thing. Um, it can be a smaller footprint like this. That's an internal circuit, which you don't need to worry about. Just put it on the PCB board, it's going to start working. Anything else? See? Here, AC? Regulated work queue, right? So regulated, not AC. Not 110, okay? It's going to burn everything on the board. And that's the input, and that's the output. So see, the single, that's a battery cell, so you can connect to here. And all your electronics will follow. Okay? Yeah, just let you know, something you probably will use it in the future. All right. Sensors, transducers, actuators. I have 3 slides. I have 3 or 4, probably 4 slides, PowerPoint files. I'm going to present to you guys in this week. So no snacks this day, but next time bring snacks over, popcorns or something. Just some introduction for the sensors and some example Arduino sketches, so you'll know how to use it, how to interface your sensor with your microcontroller in the future. And you know that, what's the name of this robot? Spot. How much? Did you see it's available already on the market? And there's one person, I forgot his name, on YouTube. He always do that unboxing. That guy, because very famous right now, and very rich as well. You see the how many subscriptions and how many views every day, every time. He probably is a millionaire already. He bought one after this is available on the market. Probably the first one who bought it, and put it at home. $70,000 US dollars. Somewhere, not as much as expensive as a Land Cruiser, but close. I would buy a Land Cruiser instead of this one. Okay, so every single robot has many sensors, as you know. There are different categories: light sensor, temperature sensor, force, pressure sensor, position sensor, speed sensor, sound sensor. And we are going to have examples for every single category for you guys. Here's the definition. Active sensors and passive sensors. What are they? So active sensors always need a power supply. A passive sensor does not need that. For example, the very simple one you have used for many times. I don't know, it deserves that sensor name, potential meters. Doesn't need a power supply. It's changing its value just by twisting the little knob, so you can change the resistance. Okay, that's the first sensor I'm going to introduce. It's called LVDTs. The full name is Linear Variable Differential Transformer. I couldn't even remember that, but I'm going to put on the quiz or exam. They're so bad. All right, linear. So there was one person asked for my help when I was in my graduate school. He's from a civil engineering department, and he was measuring the movement of the concrete or something. Since he doesn't know how to interface the sensor with my controllers, he has to ask for help from us. So I think it's better to learn whatever is more useful, and so you can. I'm pretty sure you guys, if you change your major, you can measure the concrete movement, but those guys couldn't move back to here to do this programming. So The way it works is it has the core in the middle, the bar. Okay? Somebody can, it's like a piston. You can move it back and forth, and it's going to change the magnetic field between the two coils on the top and bottom. So you power up the top coil, which is A, and whenever the core is being pulled or pushed, the output voltage at B will be changed because the number of turns of the coil in the middle is being changed, which is changing the output voltage, which is actually the current, and also being converted to the voltage output at B. So you can directly measure the voltage output to calculate back for the displacement of the core. And if you mount the core to somewhere, so you can measure the displacement of that object. That's how that works. I mean, this is a pretty common sensor in construction because this is really robust, has a really long lifespan. It's not going to worn out really quickly. Can be used in a really harsh environment, and which is still fine. So here's how you use it. So for example, we have one LVDT. What is LVDT? Yeah, linear variable differential transformer. Z. All right, so the little sensor at the bottom, and so the picture looks crap because I drew it. I'm really bad at drawing. But this is just to show you, if you have a device like this, how do you want to get the data out of it? How? We are engineers. I don't want to just give lectures in the whole semester, just tell you this is LVDT, these are the input output, but never tell you how to use it. I'm really realistic. If I don't know how to use it, I don't want to introduce that to you. Okay. These are useful. It's being powered up by 24 volts, and the output is from 0 to 10 volts. Your Arduino is being powered up by how many volts? 5 volts. So definitely 10 volts is not working. What about 0 volt? Can you sense 0 volt by Arduino? No, I mean, can you sense a 0 volt by Arduino? Can you sense it? No, not you, I'm sorry. Can Arduino sense the 0 volt? From where? From the ADC's port, analog to the A0 pin, A0 to A4, I guess. So it has 5 ADC pins as input, analog input. So the Arduino Uno does have the an analog input pins, and the script for reading that is analog read. Remember that one? The library, analog read. Just read it, and after it read it, it's gonna show what kind of number to you? 0 to where? Where? You have to think about what's the precision, what's the resolution for the ADC on the 328P microcontroller? 10 bit. So what's the range? 2 to the 10th. What is 2 to the 10th? That can be an interview question as computer engineers. If somebody in a company interview you, if they ask you, what is the 2 to the 10th, and you don't know, I won't hire you. What's the 2 to the 10th? 1024. Okay, keep in mind. 1024. So you have 1024 steps for the ADC. What is ADC? Analog to digital converter. And you don't need to know the structure of the ADC. We just need to know how to use it. Super simple. Just use the library. Analog read, one line in Arduino. Analog read, just read the voltage, and it's going to report it to wherever you want, to the memory, to the serial monitor. And the range will be 0 to another trap. 0 to where? 1024. You are fired. 0 to where? Digital, right? 0 to where? To 10? So the entire analog range is from 0 to 5 volts because that's your power supply voltage. That's the analog range. And you divide that 0 to 5 volts to how many steps? 2 to the 10th. So the final reading, if you have a 0 volt analog voltage, it's reading 0. If you have 5 volts, it's reading 1023. Making sense? Totally 1024 steps. Okay. So that's what you are going to expect for the output or for the reading for the Arduino. And the way you use it is you definitely need to power it up 24 volts, but the 24 volts is not signal, it's just power supply. It must have some kind of digital circuits inside to have the reading converted to 0 to 10 volts range. Okay? You have to use a volt divider because you cannot read 10 volts. Arduino is 5 volts. 10 volts is going to burn it down. Okay, so that's why I put a little potential meter in the middle and 10K, and I also have a 1K on the top and 1K at the bottom to just not avoid shorting this to either top or ground. So Arduino, I have A0 as the analog input, and I put a potential meter there, and the output go to the A0 pin. And then what? How do you calibrate it? I push it to the end, to the very end. Just push it to the end, and adjust the potential meter until I have a reading 0. Okay. And then I pull it to the very end as well, and adjust the potential meter in order to get a 1023. That's the full range. Wait, do I need to? No, you don't want to. No, just adjust once. So if you push it to the end, you definitely are getting 0 because you don't need to adjust the potential meter because you're outputting a 0 volts. So 0 volts, you see here. You couldn't see, but the output, when the output of the sensor is 0, the other terminal of that wire is also ground. So no potential drop across the 3 resistors. So you are getting a 0. So you don't need to adjust the potential meter. So you only need to pull it to the other end and adjust the potential meter in order to get a 1023, and that's it. And you're done for calibration. And you start trying to use it. Another one, string gauge. That's a really interesting material and useful as well. String gauge. It has all these metal wires being printed on a plastic film, pretty soft, flexible. And if you bend it in one direction, the resistance will go up. If you bend it in the other direction, the resistance goes down. Okay? How? I don't know. Somebody sells it. And it's very common and cheap. Just buy it. Okay? Since if you bend it this way, probably you are making the wires longer. If you bend it this way, they are shorter. So probably. I don't know. Anyway, we don't need to care about that. Just use it. That's a string gauge. And because it's changing the resistance, depends on the deformation. So you can use it on a load cell. Have you ever heard about load cell? Load cell. Since, for example, you want to use this one to measure the deformation. You don't want to directly use this plastic film to measure that. Since if you step onto the onto the sensor, you're going to break it. So you need a load cell. It's normally a metal thing, like for example, this kind of shape, but made in metal. And if I attach the strain gauge to here, so because it's like a cantilever structure, a cantilever, like this. And because here is a cantilever structure, so this is nothing in the middle. So if you push it, it's going to create a deformation a little bit, but not too much. But actually, that guy can sense it. That's why you attach to the back of the top or the bottom, either way. And if you step onto it, since it's metal, you're not going to break it, but there will be a little bit change of the structure, which will be converted to the strain gauge and cause that resistance change, tiny change. And you need an amplifier to amplify it and digitize it as well. So you need a sensor network, not sensor now. I'm going to introduce that pretty soon. It's called Wheatstone bridge. Anyway, so the changes of resistance over here will be converted into a voltage change, and the voltage change will be amplified. And amplified voltage change will be sensed by your A0 pin on Arduino. That makes sense? Okay. So after I have seen all these kind of sensors, you'll see that all the different types of sensors will finally get information converted to either voltage or current. So you can use your Arduino to sense it, ADC to sense it. It should be voltage eventually. If you have current signal output, you have to use an amplifier called transimpedance amplifier, TIA, to convert the current into voltage, and then ADC. Okay? If you directly have voltage, and the voltage is in the correct range, then directly connect the voltage to ADC. You're done. The ADC inside the microcontroller will directly digitize the analog signal, so you can save all these data points to the memory banks in the CPU, and you're done. They're ready to be sent to anywhere. You can use the I2C, SPI, serial, any communication protocols to do the post-processing. You're done. Okay. So now we are talking about this guy. It's converting the pressure, stress, or deformation to resistance. But however, we need something to convert, amplify, right? So if you read the bolded word, the term, it's called Wheatstone bridge. It looks like this. Oh, not there yet. Okay, so there are the load cells, different types of load cells. Every single one is different, but they are all load cells. Okay, that one. So the bathroom scale. And that little one, and you can create four, use 4 string gauges to form a four string gauge Wheatstone bridge. And the green PCB is amplifier. And you don't need to worry about what's going on inside because somebody already made it. We are going to look at the schematic person, but never mind. So you can buy that one and have the output being sent to the Arduino or any other microcontroller which has ADC on that. And that's a bathroom scale. You can make one bathroom scale by yourself. Pretty simple. That's it. That's a Wheatstone bridge. How that works? Circuit one stuff. Did you see this one in circuit one? You did? You didn't? So convert that bridge into a parallel resistor network. And the load is the V out is actually VCD. So the voltage difference between C and D is the V out. So if you have R1 equals to R2, R3 equals to R4, VCD equals to are we missing anybody? No. Okay. so I don't have to be close to the laptop. I'm recording. Whenever we're talking, we're saying this resistance rate is balanced, which means BCB equals to 0. That's the starting point you want to calibrate. You want to make this guy ready for measurement. If calibrated and BCB is 0, you're ready, because right now, before you step onto the balancing scale, it should be 0. It should be 200. Okay? What's the requirement to make that happen? Yeah, that's one thing. But in case all the resistors are ideal, given by God, ideal. So it has to be, I know it's not working. Surprise. R1 over R2 equals to R3 over R4. How many is that right? Yeah. So it's balanced. If we replace, for example, this one, either one, replace this guy with a gauge. Replace it. And then there will be a little delta R. Okay? And what's going to happen here? You're having a potential drop or potential increase. It should be an increase, increment, right? Because this guy has more voltage, more resistance, which is a larger potential share. So this guy's higher, this guy's lower. We got voltage. I can sense that voltage, amplify that voltage. Right? That's how that works. And there are a couple of ways to do this. You can have one, you can have two, and you can have three or four. The more strain gauges you have in this network, the more sensitive it will be. I'm going to show you how to verify this, for instance. Verify it. So I'm not going to write anything on the paper. You have to. All right. Hmm. Okay. So let's look at the quarter bridge first. Quarter bridge. Which means I only have one strain gauge to replace one of the four resistors. So it's here. V1 V2 R plus delta R, and its variable is changing, and I ground this guy, and here's Vx, Vex, because that's called the excitation voltage for the Wheatstone bridge. So we are trying to calculate delta V. Delta V equals to what in here? V2 minus V1, for example. And what is that? What is V2? It's Vx. Here's ground. So it's literally Vx times R plus delta R over 2R plus delta R minus Vex times what? They are equal. Then what? Is that right? Wait. No, 2R. Is this correct? No, it's not. Am I doing this right? No, I'm not. Make so many mistakes. Should we start this over? I hate it. Sorry. I was trying to do it fast, but keep making mistakes everywhere. Sorry. So go to the admission office to ask for some refund, okay, for this lecture. $20 for each of you. Which one? No, it's R over 2R. So 2 times this, right? So it's going to be 2R plus, is this correct this time? Two R plus 2 delta R minus 2R minus delta R. Okay. And I think we can ignore something. I think delta R is small compared to 2R because every time you bend the load cell, this change is tiny compared to this one. So probably you're having a few ohms plus to like several kilo ohms. So you can pretty much ignore here, but not here, since if you ignore everything, you don't have any delta R. So actually you can ignore this guy, and what you're getting is Vx times delta R over 4R. So that's a quarter bridge delta V. That's the output. Okay, that's a quarter bridge. Now we have half bridge. Half bridge. So half bridge, we're going to change these two resistors at the same time. So eventually there will be two strain gauges, and you attach these two strain gauges to the two sides of the cantilever. So for example, here, that's the wall, right? That's the wall, and here's the cantilever. It's a metal plate, something. And I have one strain gauge here, one strain gauge here. So when bending this here in this way, they are changing in different directions. This one is increasing, this one is decreasing. Is that making sense? Like this. Okay. So one will, for example, is going to do this. Another one will do this. So delta V equals to still V2 minus V1, but VEX is going to be R minus delta R over this plus this, which is 2R. Actually, this plus this, because this is closer to the ground. So this one on the top over this plus this, which is 2R. Voltage divider minus still a half. And this equals to Vx times how many times more sensitive than the quarter bridge? How many times? 2 times. You have the same delta R, but this guy will output more voltages. Okay. Now, the full bridge. Frozen again. So we're doing this. So based on your how to deploy all these strain gauges, but they are trying to do this. Okay, example. So that's a final effect. So this tool will reduce the resistance. This tool will increase the resistance. Now, delta V. Delta V equals to V2 minus V1, still Vx R plus delta R over 2R minus R minus delta R over 2R. It's going to be Vex times 2R, this minus this, 2 delta R, which is Vex. Even better. So we'll never get a chance where you are allowed to use 4 strain gauges, So when you're seeing the bathroom scale, you saw how many load cells in the corners? 4. That's why, because it's more sensitive. How many? Which one is the bathroom scale? Yeah, this one. Here's schematic. Probably around $1. Everywhere. You couldn't see that very clear, but this is clear. This one's clear. They have the metal ring. Only this spot is attached to the ring. So actually, the entire pad here is floating in the air. Well, it doesn't have any connection to the ring. So the entire pad is a cantilever structure. So when you bend it, it's going to be formed. And you insert a strain gauge inside the sensor. There are 4 of them, and connect to the sensor. Why 4 wires? What are 4 wires? What are they? Why there are only 2 wires? 3 wires here, but 2 wires here. Oh, 3 wires here. This one. The thing that there are 3 wires. There are 3 wires. Where are they? Think about it. I've never used it, but just think about it. 3 wires. The excitation, right? So, wait, it's just a string gauge. This is a string gauge. This is a resistor. Only 2 wires. I don't know what it is. It's probably just a one. It's not a wire. I'll leave the question to somebody we'll use in the future. It's pretty simple though, not a problem. Okay, so that's a string gauge. Yeah, if you look at the stiffness 3 wires, probably it's a ground, something. Okay, I don't know. Okay. Let's come back here later. So that's a quarter cell, a quarter bridge. That's a half bridge. And that's the example I just showed you. You can attach the 2 string gauges on 2 sides of the cantilever bar. And this is a full bridge. Here's the sensor. Here's schematic. So what are they? They drew this in Eagle. It's not Altium. It's the Eagle schematic. What's going on? Okay. E plus E minus. I think that's excitation voltage. the on the bottom. And A plus B minus is the output. Okay. And for the voltage being supplied, what is this one doing here? It's a low pass filter. So any voltage surges will be blocked by the inductor. So any surges could not go here or could not go back, protecting the circuit. Not doing anything else other than that. And these are small seam capacitors, so like reservoirs, also low pass filter as well, for the charges. So signal goes into here, so that's the input, is that right? So here's the differential input. That's a 2 CNT. That's a CNT. That's something feedback. I think it's for some calibration inside the chip. We don't need to know that. Normally they will provide information. Like you need, for example, they'll give an equation for what are these two resistor values to pick up for the system. It's going to be a voltage divider to divide the power supply to a certain voltage, like a voltage reference for the chip. That one is doing nothing to a signal. So here's a differential signal comes out. That's a VC and VE. So here, the capacitor here is also blocking any sharp surges. We are having two DC steady voltages go into here. So two DC voltages get inside, being received by this chip. What's the next? Amazing. What's inside the block here? What's this guy doing? We're looking at the schematic like this. After you learn this class in computers, you are starting learning how to read the schematic like this. Even though it has so many other like caps, adapters, but actually they're not doing anything for the signal. And they're just filters. So here's a real thing. Goes into the chip. That's a signal. Two DC voltages. How to process it? What's next? Huh? Comparator, you are getting a digital output, but you need an analog output. You can't just get 1 and 0. It's differential amplifier. All time, but two inputs. So it's calculating the difference between those two inputs, and then ADC as well. After that, after the amplifier, the differential amplifier, ADC. So that's it. See, VCD, the VCD, the VCD goes into here, two steady DC voltages, and it has two channels. So actually, it can have two different Wheatstone versions. I only use one here. Have two channels. You have a multiplexer to pick up which one you want to use. More function. And programmable gain amplifier. We can pick up 32, 54, or 128 different gains. Amplifying the difference between those two voltages. Why difference? Why do you want to find out the difference between those two voltages? Why you care about the difference between these two voltages? It's correlated with the weight, with pressure. That's what we just calculated on the paper. Right? Calculate the VCD, the delta V. That's the two voltages. You have a differential amplifier to do the subtraction and also amplify. What was next? No. Oh, amplify. Yeah, after amplification, yes. How many bits? 24. Is that low or high? Yeah. How many bits does the Arduino have? 10. This is 24. Come on. 2 to the 24. What's that? Like huge. It's pretty precise. It's a really precise ADC, but which can resolve really small pressure they can design skills being used in the lab. Like marrying chemicals. You want to use really not sensitive ADC to marry chemicals in the lab. Right? Very sensitive. You need a sensitive ADC. And this thing here is called delta sigma, even though it's a sigma delta, but actually the name of that ADC is called delta sigma ADC. There are several different types of ADCs. If you go to graduate school, you will learn advanced electronics. They'll teach you how to design ADC in IC level. You go to UNLV for graduate school, you'll learn a lot. You'll probably do ADC. That professor is very good at it. We don't need to worry about it. We just need to use it. And digital signal comes out, and you need a digital protocol. And it's not a standard protocol. I think it has its own communication protocol. So what's a protocol? Yeah, function, right? So if there's nothing happening, for example, 2 wires, microcontroller 1 sensor, they both have this protocol. 1 signal line, 1 clock line. You see CK is clock. So even though I haven't used this before, but I know this is digital output. There's a clock. I have 2 wires. Here's a sensor. Here's a controller. And the clock will be shorted together that way, so they can share the same clock. They're doing the same job at the same pace, on the same page. So the clock is triggering the behavior on both sides at the same time, and data. So based on the clock, the data will be sent to or be received by the 2 different parts. I'm pretty sure you can find a library online or Arduino. Find a library and do it. First thing. If you want to program the details about it, you have to look at data sheet of at which time point it's doing what. Look at the time. I forgot how to say it in English. Timing diagram. Yeah, timing diagram for SCK and DF. So what's going on in there for every single moment? What this one doing? What this one doing? So then you can program to make this happen. Okay. So data from the resistance difference to the digital output to the microcontroller. That's how that works. It's pretty much everywhere for any kind of sensors right now. As long as the digital sensor is going to work in this way or a similar way. Okay. And as long as there's a digital sensor available, use a digital sensor in the future. Even if you compare to 20 years ago, it's not even like this right now. So there are so many digital sensors available on the market. If you are using a thermocouple, wires, do you have a digital sensor? No, it's just like 2 wires, right? Having a voltage difference on the 2 terminals. It's going to be a voltage difference overall after at the 2 terminals. If you are using a thermocouple, there will be a lot of work to do if you do not use a digital sensor after that. You have to design an amplifier. You have to probably buy an ADC, and then ADC to a microcontroller. If you grab a digital temperature sensor, you connect to your Arduino, you can make it work in 5 minutes. So as long as you have a digital sensor available on the market, use a digital sensor. Okay? Same like this. Just use this one. I think so if you want to build a downstream scale, for example, for a specific application. For example, I could give you a project. I won't. I'm not going to build a downstream scale. That's something horrible for robotics class. For example, right, you are making a downstream scale. Let me know how far you want to make it. Start from scratch. Nothing. And I'm being asked to build a downstream scale. What's the first step? Find buy a string gauge, buy a low cell from Amazon. $5 got 4. Then got a wire comes out. What's the next? Why is this really sensor? I mean, this is great. $5. Why? So signal from the low cell from the string gauge, you have to connect to this chip. This chip pretty much does everything. From voltage, amplify it, digitize it, and output to my controller. And take your Arduino board from the box, and Google examples about string gauge or something. Download, run, done. After it's done, everything's built on the breadboard with all the jumping wires. What's next? PCB. And what do we need for the PCB at the very beginning? Power. Put a connector. Place connectors into the schematic view. Place the power cells. And place these parts. And connect to PCB. Go to a layout view. Arrange it. Send it to China for fabrication. $5 for 10 pieces. Got the boards. And solder all the parts to the boards. And probably design a little container or case. You can get a mold overseas as well. It's pretty cheap. Just let them know your design, what you want to do. You can make a mold and make a box for you. If you have a little display or some push buttons, you can probably design some functions in your controller, like interrupts. There's always scanning all the push button skills and no push button activities. So when you push it, you can change something on the monitor, whatever, or reset, something like that. And assemble everything together and sell it. All right, that's everything for today. We'll see you on Friday. Don't forget about bring snacks.